Hello and welcome back. In this chapter, we're going to study two-dimensional motion. So that means we're going to take what we already know about motion in a straight line in one dimension. We're going to learn how to apply that to objects that move in more than one direction. And in particular, in today's lecture, we're going to learn about a very specific type of two-dimensional motion called projectile motion. So let's think about what would happen if you had constant acceleration in both the x and the y direction. So we already know how to deal with situations in which you have constant acceleration in either x or y, but what if you had an object that was moving in both of those directions simultaneously with a constant acceleration in each direction? Well, in that case, everything that we already learned from chapter 2 about the kinematics applies, but it applies to each direction separately. So it applies to the x component of the motion and it applies to the y component of the motion. So what we have to do in problems that involve two-dimensional motion is we have to separate out what's happening in the x direction from what's happening in the y direction. And those same kinematic equations that we've already learned, they still apply in both directions. But you have to be really careful that everything that you have in the x direction is treated completely separately from everything that is in the y direction. So for example, you couldn't have a position in the y direction combined with an acceleration in the x direction all in the same equation. Those would have to be separate. But the one thing that does tie them together is the time. So it's like two independent motions if they're doing these at the same time. So the time that something happens is the same. So that's the key thing. And as we go through these problems today, always keep that in mind. The thing that ties x to y is always the time. So let's look at a little bit of a quick review. If we had a velocity, as shown in this picture, v1, and you had an acceleration pointing downward, what would be the velocity immediately after this? Remember that the velocity after this is equal to the initial velocity plus the acceleration times time. So we can think about adding this acceleration vector to that initial velocity vector, which is going to tell us that after a certain amount of time, our new velocity is going to be like this. So you had a velocity going directly to the left, the acceleration is pointing downward, it's going to make that object turn and move downward. So now it's not going in the same direction as it was before. So now let's turn our attention very specifically to projectile motion. So what exactly is a projectile? That's the most important thing to talk about first. Well, a projectile is something that moves under the influence of only gravity. But it's different from free fall because in this case, objects are moving in two dimensions. So good examples of things that we would consider projectiles include baseballs, tennis balls, basketballs, golf balls that you hit through the air. So there are a lot of balls involved in various sports. All of those are projectiles. We can also think about things like an arrow shot from a bow. Even a bullet shot out of a gun is a projectile because it's moving under the influence of gravity and it's moving forward at the same time. The way that we are going to solve problems involving projectile motion is really similar to the way that we did for free fall, but now we're going to also have to include an x direction motion. But the good thing here is that there's no acceleration in the x direction. Whenever something's in free fall, or whenever it's a projectile that's moving in two dimensions, the only force that acts on it is gravity, which means the only acceleration is directly downward in the y direction. So that makes it really easy because our x motion is constant velocity. The y motion is constant acceleration. Another important thing to remember about projectile motion is that we're going to ignore air resistance. When you have situations in which there's a significant amount of air resistance, then gravity is no longer the only force that really acts on these objects. And that can change their trajectory fairly significantly. So for now, we're not going to include those situations in which air resistance might play a big effect. And if there's no air resistance, and if gravity is truly the only force acting on it, then all projectiles are going to follow a shape that looks like a parabola. Follow a parabolic shape like this. So let's look at what happens right at the beginning, because this is usually the beginning of a problem. You launch a projectile or you throw it. In this case, we throw a basketball. One of the very first things that we usually want to do is to take that initial speed at which the ball is thrown and break that up into two components, x and y components using vector algebra that we have already learned in the last chapter. So what we first want to do is take that initial speed and we want to multiply by cosine of the angle to get the component in the x direction, and we want to multiply by sine of the angle to get the component in the y direction. Now once again, just like it's true for all other vectors that we have worked with for this entire year so far, if you use these two equations, you want to make sure that you're measuring the angle right here from the x-axis. If you measure the angle from the y-axis, you will have to change it up a little bit. Your sine and cosine will be reversed. So it's easiest to always make sure that the angle that you're measuring is from the x-axis. So this is typically the very first step in any problem. If you're given an angle, you're given an initial speed, you want to separate out x and y, and then you want to keep those separate for the remainder of the problem. Now, as the ball proceeds through the air, we know that gravity acts on it. And gravity is the only force that acts on it. By definition, that's what makes it a projectile. So therefore, projectiles don't have any horizontal acceleration. So we can always say that the acceleration in the x direction is 0. And that makes things a lot easier for us because we don't have to worry about acceleration in that direction. We only have one acceleration, and it's only in the vertical direction, never in the horizontal direction. And in the vertical direction, it's always equal to exactly minus g. If you don't remember, g is 9.8, assuming that we are on Earth. And right now we're assuming that all these problems are on Earth. So let's look at what that would look like in practice. So remember that all projectiles follow a parabolic trajectory. So let's follow the projectile along different points in its trajectory and see how its velocity changes. So imagine that you have a projectile that's launched with an initial velocity given here, 9.8i plus 19.6j. So in this case, we didn't have to break the initial velocity up into components because it's already given in terms of components. If you were given a magnitude and direction, the very first thing you want to do is separate those two components. Here we already know that in the x direction, it's 9.8. In the y direction, it's positive 19.6. Now what happens after 1 second? Well, after 1 second, the ball has obviously moved upward into the air, but what's happened to its velocity? Well, in the x direction, nothing. Notice that here, 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 and here, and even here, the x velocity remains 9.8 meters per second. It does not change the entire time, and that is because there's no acceleration in the x direction, meaning that there's no change in the velocity. If there's no acceleration, there's no change in the velocity. The same cannot be said for the y motion, though, because we know that the acceleration in the y direction is negative 9.8 meters per second squared. So what that means is that every second, the velocity decreases by 9.8. So that after 1 second, we've gone from 19.6 down to 9.8. After 2 seconds, we've gone from 19.6 to 0, and we only have a horizontal component at the top. Unlike free fall, the ball does not completely stop at the top because it's still going forward. But the vertical motion, the up and down motion, is 0. There is 0 vertical velocity at that point. And then it turns around, and as it comes back down, it still changes by negative 9.8 every second. So now we go down to negative 9.8 and then finally negative 19.6. So it follows like the same pattern going up as it does coming back down. Let's look at a few questions here, just thinking about projectile motion and reasoning through some problems before we do an entire problem with some math. So let's look at a simple situation here. It says a heavy red ball is released from rest 2 meters above a flat horizontal surface. At exactly the same instant, a yellow ball with the same mass is fired horizontally at 3 meters per second. Which ball hits the ground first? So think about this. Which ball do you think would hit the ground first? The red one dropped from rest, the yellow one shot horizontally. Most people are tempted to say that the red ball hits first. Intuitively, you think the red ball is not moving, it's just going straight down, so it's going to hit first. But that's incorrect, because the yellow ball only has a horizontal velocity to start with. Its vertical velocity is also 0. So the initial velocity in the y direction for the red ball is 0, and the initial velocity in the y direction for the yellow ball is also 0. So what that means is that the balls fall at the same rate. The acceleration in the y direction is exactly the same. So the yellow ball is going forward at the same time that it's falling. But the fact that it's going forward does not affect how quickly it's falling. It's still falling at the same rate as the red ball. So we could tie it every moment in time. We could draw a direct line between where the red ball is and where the yellow ball is. The yellow ball is moving forward, but it's not falling any faster or slower than the red ball. And this is because what happens in the x direction does not affect what happens in the y direction. We can treat these motions as entirely separate. The only thing that connects them is that they're happening at the same time. So whatever happens in the x, we don't have to use that information to determine what happens in the y, except for the fact that they're at the same time. Following up on that, let's look at another quick question. This one says a 100-gram ball rolls off a table and hits 2 meters from the base of the table, and then a 200-gram ball rolls off at the same table with the same speed. Where does it land? Well, do heavier objects fall faster than lighter objects? No. Galileo established hundreds of years ago that that was incorrect. All objects fall with the same acceleration if the force of the air against them is not very large, and it wouldn't be in this case. They're only falling for 2 meters. So whether the ball is 100 grams or 200 grams, it falls at the same rate, which means that it's going to hit the ground at exactly the same spot. Let's look at one more question. And this one's kind of tricky. So a hungry bow and arrow hunter in the jungle wants to shoot a coconut. So he points his arrow directly at the coconut, but the coconut falls from the branch at the exact instant the hunter releases the string. Is the arrow going to hit the coconut or not? Let's think about this. So you aim directly at the coconut, you shot the arrow at the coconut, but the coconut falls at that same instant. If you didn't have any gravity, your arrow would go straight up to where the coconut was and would hit the coconut if it was still on the tree. But that's not what happens. When you shoot the arrow goes up, but it immediately starts slowing down. So it actually never gets up to the point where the coconut was up on the tree before it turns around and starts falling back down to the earth. What's happening to the coconut during this same time? Well, it's also falling, right? At the same time that the arrow is falling, it's in free fall. It's a projectile. The coconut is also in free fall. So the arrow and the coconut are both falling at the same rate. So without gravity, that arrow would go straight up towards the coconut. But with gravity, it curves downward. And the coconut is still going to fall right into the arrow because the coconut and the arrow are falling at the same rate. They're slowing down at the same rate, just like the two balls did that we looked at earlier. Now, what would happen if the coconut stayed in the tree and you aimed your arrow directly at it and shot it and it didn't fall? Well, then you would totally miss the coconut. Your arrow would go way under the coconut. What would you have to do if you wanted to actually hit the coconut up in the tree? Anyone who's ever shot a bow and arrow knows that you would have to aim above the coconut, right? Why is that? Because the arrow is going to fall back down towards the coconut. If you aim right at the coconut, unless the coconut falls, you're out of luck. It's not going to hit. So summarizing everything we know about projectile motion so far. Again, projectile motion is defined as motion that is only under the influence of gravity, but is also moving in the x and the y direction. Mathematically, because there's only acceleration in the y direction, it means that in the x direction we have uniform motion. And we know how to calculate that initial velocity. In the y direction we have constant acceleration. And we've already looked at, back in chapter 2, how to deal with both of those situations. How to deal with the situation where you have uniform motion, and how to deal with the situation where you have constant acceleration. The key thing, as I've said earlier, is that the same time interval has to be applied to both objects because they are both directions. It's one object, but the same, the two different directions. Those two motions are happening at the exact same time. One thing I'll point out is that this is a very useful model, but it is obviously limited, right? Everything that we developed here assumes that there is not a lot of air resistance. If there is a lot of air resistance, then we have to treat it differently, and we'll talk about how to do that later. So how do we solve projectile motions? First of all, determine if it's reasonable to ignore air resistance. How can you tell if it's reasonable to ignore air resistance? Well, in many problems, it will tell you that air resistance can be ignored. Otherwise, you have to look at the situation. And in the real world, this is true as well. If an object is not moving very fast and it is pretty aerodynamic, like it's round and it's not flat, then air resistance can probably be neglected. So things like shooting a basketball, dropping a wadded up piece of paper, those things you would have not much air resistance. If something moves very quickly, even something that's really aerodynamic can have large air resistance if it's moving quickly. So if I drop a ball from the top of the table, air resistance is negligible in the time it takes to fall to the floor. If I drop a ball from an airplane, air resistance is eventually going to be important as the ball goes faster and faster and faster. So high speeds or low, the shape can make it have a low aerodynamics, where it's going to catch the air more. Either one of those things is going to mean that you really can't ignore air resistance. But once you've established that it's okay to use the projectile motion model, you want to establish a coordinate system. Typically, we go with the x-axis horizontal, y-axis vertical. You want to identify all the symbols, determine what that's trying to find, and try to separate that initial velocity into two different components. Then we can apply equations separately for each direction. For the x direction, we have constant velocity. So there's really only this one equation that we need to know. For the y direction, we have constant acceleration. So that's where we can use any of those three kinematic equations. In general, this one's going to be the one that we'll use the most, the first one. Okay, now let's try to put this all together and solve a problem. In this problem, it says a stuntman drives a car off a 10-meter high cliff at a speed of 20 meters per second, and we want to try to figure out how far does the car land from the base of the cliff. So the first step is to draw a quick sketch of the situation, labeling all of the information that we know and what we want to find. So I draw the cliff here. So here's my car. It's going to start with an initial velocity, and my velocity is in the x direction to start with. It drives straight off the cliff. Of 20 meters per second. I'm going to put my origin right at the bottom of the cliff so that I don't have to have any negative numbers. And this is the origin. And that means that my initial x position will be 0 and my initial y position will be 10 meters. And as the ball falls, or as the car falls, it's going to come down to the ground. So the final y position will be 0. The final x position is unknown. We also know that because it's in the air, its acceleration in the x direction is 0, and the acceleration in the y direction is minus g. Now, I think it's a good idea at this point to make a little table of what all we know about the x and the y directions. So in the x direction, what do we know? Well, we know that the initial x velocity, initial x position is 0. The final x position, we don't know. We know the velocity in the x direction is 20 meters per second, and that's initial, final, and everywhere, because we also know that the acceleration equals 0. What about the y direction? Well, we know that the initial y position is 10. We know that the final y position is 0. We know that the initial velocity in the y direction is 0 because it starts going straight off the cliff. And we know that the acceleration is minus g, which is minus 9.8 meters per second squared. And we know that the same time applies to both. So we have two equations that we can use here. We have constant velocity in the x direction, and in the y direction, we have constant acceleration. And what do we do with this? Well, the next step is usually to take what information you have and try to use that in these equations, and remembering that we're trying to solve for this value. So we know that the initial position is 0. We know that the velocity is 20 meters per second. We don't know delta t. Right? But we know that delta t is the same for x and y. So what we can do to find delta t is we can come over to our other equation. And we can solve this one. So we have this is 0, this is 10 meters. Our initial velocity is 0. Our acceleration is negative 9.8 meters per second squared. That's delta t squared. So what we need to do is then to rearrange this equation to solve for delta t. So we can move the 10 to the other side. We can divide both sides by 4.9. To get that delta t squared is 2.04 seconds squared. And then take the square root of that to get that delta t is 1.43 seconds. Now, we can come back over here and use that to find the final position. So our final position at the bottom of the cliff will be 20 meters per second. It's going 20 meters per second forward every second, so we just need to multiply the time that it's in the air. 20 meters per second times 1.43 seconds gives you a final position of 28.6 meters. And that's our final answer. So in every problem involving projectile motion, which we'll practice a lot more in class, they're all going to follow the same basic pattern. So we're going to separate out x and y direction as much as we can. We're going to write out an equation for x, equation for y, and putting these together is usually going to involve solving for time in one equation and then using that in the other one. Tomorrow in class, we'll go through a lot more examples of these types of problems.